Yeah, hi, welcome everyone. My name is Thomas, and today I'm going to present on data-driven high-resolution ocean wave forecasting and extreme wave prediction. So this talk accompanies the following publication written or authored by myself and Professor Balachandran from the University of Maryland in College Park, and it appeared in 2023 in Ocean Engineering. So just to motivate the topic of extreme waves, so an example of extreme waves, what we are after are rogue waves or freak waves. So those are waves which are significantly larger than the neighbors. So you can see here for an example. So for this is a time series of sea surface elevation, so ocean waves. And we see that for the majority of the time, the sea surface elevation is rather limited. However, here we see that suddenly a large wave appears and disappears without leaving any trace. And this is an example of a rogue wave. And just to give you a bit more of a visual impression, I brought along this video here of a freight ship in the ocean. And we can see it is steering to some waves, but nothing too outrageous. And now after that, we can now suddenly see that here on the right-hand side, a large wave appears and hits the ship. And we can already sense from this videos that the enormous forces acting on the ship's hull, which is of course not optimal. And while this vessel could continue its journey without any visual harm, others were not so lucky. So the loss of supercarriers and also serious injuries of sailors and passengers have been linked to the occurrences of rogueways. So this motivates the study of rogueways, and in the following, we are particularly interested in forecasting such events. And in the following, we will take a data-driven route to forecast extreme waves. And so essentially, we want to come up with some kind of model which takes in past sea surface elevations to past wave data and produces or forecasts future sea surface elevation here. So this is my model now. We take past data in and we produce future data. So a forecast. And in this data-driven forecasting, no matter how you twist and turn the problem to do data-driven forecasting, we need data. And we found some data, useful data, in provided by the CDIP, a program run by the Scripps Institution of Oceanography in San Diego. And they provide data from a buoy network of overall more than 160 buoys. And those are primarily located at the shores of the continental US, so West Coast and East Coast. But we also see some buoys here in the Pacific. And those are used to record various sea state parameters, but also sea surface elevation, which we are after. And a nice thing about this data is it has a sampling rate frequency of about 1 Hertz, which is enough to, or so which is enough to resolve individual waves. So wave periods are in the second range. So this is enough to resolve those kind of periods of ocean waves. And if we are after forecasting extreme waves, we need to resolve individual waves. And overall, we have quite a lot of data. So if we stitch all the data together provided by the 166 individual buoys, we get a time series of about 880 years sampled with about 1 second sampling, one hertz sampling rate. So this is quite a lot of data. And just to back to the previous slide, we want to do data-driven forecasting. And I'm sure you all paid attention over the last year. There's been an advent of machine learning methods, more particularly neural networks, which come with the promise that they can do such data-driven forecasting. And based on the universal function approximation theorem, theorem, they say now that they can approximate any functional relationship between the past data and the future, given that there is enough data for fitting. But I just told you we do have a lot of data. So why not using one of these well-developed neural network approaches? And the outcome is quite common with, so we've tried, for example, STM networks, temporal convolutional neural networks, encoder, feed-forward networks, and also transformer networks. But we overall, for all these models, we see that the forecasts, they quickly deteriorate and are useless after a few seconds. So we had to do a little more work, and I'm just going to give you an overview now in the next slide. So now instead of going from here, from the sea surface, the measured sea surface elevation, and directly producing a forecast with a neural network or a data-driven approach, we had to do a little detour. And this detour consists of three steps. So the first step is the decomposition step, then we have a forecasting step, and then the synthesis. And I'm going to talk to you in the next couple of minutes a bit about the decomposition and the forecasting aspect. So with the decomposition, we were inspired by the essence of all ocean wave models out there, and also state-of-the-art operational ocean wave forecasting models, which decompose the ocean here in a set of rapid oscillations, so rapid up and downs, which is and with slowly varying spectrum and amplitudes. In essence, this inspires the following model here, where we have the rapid oscillations modeled with cosine and sine functions. And now the slowly varying amplitude and spectrums are captured by this by the time variation of the amplitudes uj and vj, which are allowed to vary on time, but slowly, which is modeled with the small parameter epsilon here, which is small. And to fit this model to data, we utilize the following cost function, which consists of two terms. So the first term enforces that the fitted model accurately represents the measurement. So h is going to be my sea surface elevation measurement from the buoy. The second term penalizes variations in the amplitudes. So these amplitudes are allowed to vary in time, but every time variation is penalized, and this penalization is scaled with a small parameter epsilon. So every time, so every variation in time of the amplitudes is heavily penalized. So the second term, in essence, enforces slowly varying amplitudes. So the model now is linear in the amplitudes uj and vj, but nonlinear in the frequencies omega j. And so if one tries to find a minimum for the following cost function, one has to solve a nonlinear function optimization problem. And I'm not going to go into the details here, but in the paper we sketch a way how to find the approximate minimum which worked for our cases. So now, assume we have succeeded into fitting the model to a given sea surface elevation, let's say here of 3 minutes. Now, to do forecasting, I need to know what happens after this fitting interval. So what happens after 3 minutes, so after 4 minutes, after 5 minutes, and so on. And to extrapolate this fitting function outside the fitting interval, the frequencies, they remain constant as the model predicted by the model. However, the slowly varying amplitudes need to be extrapolated outside the fitting interval. And to do that, we use data-driven methods now. That's where the data-driven forecasting comes into play. And we use general like linear autoregressive models, and we also use recurrent neural networks with LSTM cells. And both of them are essentially interpolation methods with limited extrapolation capabilities. However, we can already picture now that an extrapolation here of the slowly varying amplitudes seems much, much more promising than an extrapolation on the rapidly varying sea surface elevation, as we have attempted a couple slides earlier and failed. So, and generally, we see that the decomposition into something slowly varying increases the extrapolation range of this data-driven black box methods. And just to show you some results now for ocean wave forecasting here. So this is a buoy, San Nicolas Island off the coast of LA. And we're going to see here a bunch of forecasts. So this is LSQ and DMD. These are linear models, and LSTM is where we utilize a recurrent neural network with LSTM cells for the forecasting task. And we can see that all those methods outperform the benchmark, the relevant benchmark, by about 30% on the average wave height error. If we now wonder about the highest wave, we can also see that the LSTM here clearly outperforms the linear models. And the nice thing about this model is in some sense it is data driven, so it's very flexible and does not require location specific tuning. So we can apply the same modeling approach to different buoys. For example, Maui in Hawaii. We see a similar trend that the LSTM kind of outperforms the benchmark by about 30% and also similar compared to the linear models. And now, marching forward to yet another buoy, we go to the Onslow Bay in North Carolina, North Carolina. And this is the difference here is that this buoy now is in shallow water, so 30-meter water depths, whereas the other two buoys are in 200 or even more than 200 water meter depths. So different physical aspects come into play as one marches into shallow water compared to the deep water here. However, we again see that our STM network accurately predicts the upcoming ocean waves and improves the benchmark by about 30%. So the model we have obtained is quite universal for and can be employed to any buoy location we have tried so far. Just to connect back to the beginning, if you wonder about rogue wave forecasting, so here is a forecast of a rogue wave. So in blue is the ground truth, red is the fit, and yellow is the forecast. We have forecasted the rogue wave in 1 minute in advance, while the full extent of the rogue wave is clearly underpredicted by the data-driven forecasting machinery. We can see that we correctly predicted a rise and a decay in the envelope for this rogue wave. So just to conclude, I have presented a data-driven ocean wave forecasting approach in which exploits the essence of common ocean wave models that decompose the ocean into a set of rapid oscillations with slowly varying amplitudes. And this approach in general is capable to produce accurate high-resolution forecasts. And I haven't talked too much about it in this talk, but in the paper you find more detail that these forecasts are actually also quite computationally inexpensive, so they can be obtained in real time. So not much computations are involved. If you want to know more details, you're very welcome to read these publications or reach out. And in the future, we are planning to further explore or further focus on rogue wave forecasting with this approach, or even march to different applications where this kind of decomposition into a set of something fast scales and slow scales is rather universal in engineering, physics, and also applied science. So then a similar approach might also apply to different domains there. I hope you enjoyed the talk. If you have any questions or you want to reach out, feel free to shoot me an email anytime. Thank you very much for listening.